Hi, my name is Jim Pinkelman, and I'm going to give you an introduction to estimating probability using Bayesian techniques. Over the past few years, you've undoubtedly seen a rise in the number of articles, discussions, and books that talk about data analytics and statistics. And from time to time, I expect you've run into references to Bayes' theorem, or Bayesian statistics, or Bayesian inference. I thought I'd provide an example to describe what this means. This is truly just an introduction, and as a result, I'll make some generalizations and some simplifying assumptions along the way. I'll use a little bit of math and statistics, but for the most part, I'm going to stay away from an equation-centric approach to this explanation. My hope is to give you an intuitive sense for what this means, and that this will be useful to you in the future. So let's start with a very simple but practical description. Bayesian techniques are a method to use a new piece of evidence to revise an existing probability estimate. And in this example, this is exactly what we're going to do. We're going to start with a probability estimate. We're going to acquire new information, and we're going to use that information to revise our estimate of the probability. I live in Seattle, Washington, and in Seattle we talk about the weather a lot. Typically we're talking about whether it's going to rain on a particular day or whether it's not going to rain. While a day without rain doesn't necessarily mean it's going to be sunny, for the purposes of this example, I'm going to use the word shine for days that it doesn't rain, and rain for days that it does. I'm also going to assume that it only rains or shines. It's one or the other. Anyone who's lived in Seattle knows that the months of July, August, and September are the best months weather-wise. The temperatures are usually in the 70s, the humidity is low, and most days it does not rain. So I'm going to use an example of the month of July. If you look at historical weather data for July, you'll find out that it rains 16% of the days and shines 84% of the days. Now let's imagine it's May, and you're thinking of going to a concert on July 17th. I'm going to ask you a question. Given what you know now, what is the probability that it's going to rain on July 17th? Well, in May, 2 months before the concert, when you buy the tickets, you only have the historical data, and you should conclude that there's a 16% chance that it will rain on July 17th. Let's consider this our initial probability estimate. And if you remember from our description, we're going to update this estimate with additional information. Well, what additional information might we get? Let's move forward in time from May to July 14th. It's 3 days before the concert. We certainly could go get a weather forecast and consider this as additional information. When we do this, we learn two things. First, the forecaster is predicting rain on July 17th. Second, we also realize that weather forecasts 3 days in advance aren't always correct. Let's assume we know the track record of this forecaster well. And we know that regardless of whether it will rain or shine, this forecaster will provide the correct forecast with a probability of 75%. Therefore, the forecaster will provide the incorrect forecast with a probability of 25%. We now have an initial probability estimate and additional information which should help us. So let's ask the question again. Given everything that you know now on July 14th, what is the probability that it's going to rain the day of the concert? It's more complicated now. We have two pieces of information that seem to conflict. We have the historical data and we have the weather forecast. However, we also know more information, and we should be able to use this to come up with a better estimate of whether it will rain. First, let's consider the historical data. The historical data tells us that of the 31 days in July, it's going to rain 16% of the time. This translates to about 5 days, and here are some representative dates. 84% of the time it will shine, and this translates into the other 26 days in the month. Now let's talk about the forecast. Remember that regardless of whether it rains or shines, we know that this forecaster will provide the correct forecast with a probability of 75% and an incorrect forecast with a probability of 25%. Let's keep that in mind and look at the 5 days where it does rain. On these days, a correct forecast is one of rain. This happens 75% of the time, or about 3.75 days. An incorrect forecast will predict shine, and this happens the other 1.25 days. We'll mark these rain forecasts with a rain symbol. And use suns to indicate a shine forecast. We can also look at the 26 shine days. Here too, we get incorrect forecasts 25% of the time. So I'll mark those out. This is about 6.5 days. On these days, the forecaster will predict rain. The other 19.5 days, the forecaster will correctly forecast shine. Now, I want you to look at this picture for a moment, because there's a really interesting aspect of it that I think provides a very visual and useful insight into Bayesian statistics. The forecaster actually provides a forecast of rain on more shine days than they do on rain days. There are 6.5 days with a rain forecast down here compared to 3.7 days up here. This observation and calculation is possible with Bayes. I think it's useful to reread the description that we created at the beginning of this. We said that Bayesian statistics provides a method of using a new piece of evidence to revise an existing probability estimate. This example of forecasting the weather is very convenient because it fits our scenario. We start with a probability estimate using historical weather data, and we acquire new information, a weather forecast. We want to use this information to update our probability estimate. So let's look a bit more closely at the numbers and answer the question that I've posed twice now. There are 4 possible outcomes here. These top 2 are a situation when it actually rains, and the bottom 2 are for shine. The first outcome is that it rains on July 17th and the forecast is for rain. I've used a green box to indicate that the forecast is correct. The second outcome is that it rains on July 17th, but that the forecast is for no rain. And I used a red box to indicate the forecast is not correct. The third is that we get shine on July 17th and the forecast is for rain, and that's an incorrect forecast. And the last is that it does not rain on July 17th and the forecast is for no rain, a correct forecast. To get the probabilities of each of these outcomes actually occurring, I simply multiply the 2 probabilities. So this first case is 16% times 75%, which equals 12% with a little bit of rounding. The second case is 16% times 25%, which equals about 4%. 84% times 25% equals 21%, and 84% times 75% equals 63%. We've assumed these outcomes are mutually exclusive. This means that only one of these outcomes is possible. Therefore, you can think of these 4 outcomes as the entire world of possibilities. The value of Bayes is that we take into consideration additional information, and in this case, the additional information is a forecast of rain. The existence of this rain forecast effectively eliminates 2 outcomes from the world of possibilities. I can eliminate the 2 outcomes where the forecast was for no rain. And now I can see that there are only 2 outcomes remaining. The outcome of rain with a rain forecast and the outcome of shine with a rain forecast. Now I want to consider these 2 probabilities relative to each other. And just looking at these numbers, I can see something interesting. I can see that this second outcome is about twice as likely as the first. In practical terms, this means that despite a rain forecast, it's nearly twice as likely that it will shine on July 17th. Now I want to go back and accurately answer the question that we've been considering. Given all the information we have, what is the probability that it will rain on July 17th? To do this, I need to do a little bit of math. I need to divide the probability of the outcome that I'm interested in by the sum of the probability of all possible outcomes. From the calculations on the previous slide, I have 12% up here on the numerator, which is the probability of rain and a rain forecast. I have 12% plus 21% on the denominator. This gives me the answer. There's a 36% chance of rain on July 17th. As you would expect, you can see that this 36% is higher than the historical data, which says 16%, but it's lower than the 75% based only on the forecast. The implication of Bayes is even more apparent and interesting if I choose slightly different starting conditions. Imagine a location that's much more arid, say a desert, where the historical probability of rain is very, very low. Let's use 2%. If we translate this into July calendar days, we see that the vast majority of days we will get shine. So now let's add the forecast. Regardless of whether it rains or shines, the forecaster will provide the correct forecast with a probability of 75%. What I'll do is mark out the 25% days where the forecast is then incorrect. And now, like on the previous slide, I'm going to convert this information into forecasts for each representative day. I know I did that quickly, but notice up here on rain days, the correct forecast is a rain forecast and an incorrect forecast is a shine forecast. Down here on shine days, the correct forecast is shown with suns and incorrect forecasts have raindrops. I'm not going to do the math in this case because I think this picture drives home the point better. I can see from this picture that I will get a rain forecast much more often on shine days than I will on rain days. Slightly less than 1 up here and more than 7 down here. What's so interesting is that almost all of these forecasts come on shine days. Using a Bayesian approach, we have a method of combining our initial historical probabilities with a forecast probability, and this helps us come up with the most accurate understanding of the situation. In this case, I see something that isn't highly intuitive. Most of the time, our rain forecast will actually happen on shine days. Thank you. I hope you found this talk both interesting and useful. The proliferation of data and the availability of computing power is increasing the influence that data analytics, statistics, data visualization, and machine learning is having on our lives and on our society. There's some great information out on the web that provides more details and different explanations and aspects of Bayes, and I encourage you to dig into this material.